All right, welcome to Chapter 6, Section 4, called Dilations. This is for Math 8. So a couple things you're going to see on your screen here. The first thing you're going to see is a due date. I don't see that on the teacher's preview here, but you'll see it on your student screen. The second thing is the number of attempts. You always have unlimited attempts on tests, homework, and quizzes. Number of questions just tells you how many questions are on this assignment. Grading policy is best score, so whichever attempt is the best one is the one you keep. And partial credit is always enabled, so if you get 1 of 5 questions correct, you get credit for the 1 question, or however many you've answered correctly. Down here it says, please remember, once you start the homework, you must finish it before you can work on anything else. What that means is once I click start, down here in the bottom right-hand corner, you will see a submit assignment button. I don't see that on the teacher preview here, but you will see it on your screen. And you want to click that button before you move away from the screen. So I don't mean like from problem to problem, before you close the screen, like clicking the little red X or closing your computer. You want to click the submit assignment button. Because number one, if you don't click the button, the system is going to lock you out of all of your other assignments, assuming you want to leave this attempt open. You have unlimited attempts. There's no reason to leave it open. Go ahead and click the button so that you're not locked out of topics or anything like that. It'll save your place, so as long as you have a little green check mark here, it'll save your progress. It just starts you up wherever you left off. The other big thing that this does is it affects the gradebook when you click a submit assignment. So your teacher can actually see what you've been working on. Before you click that button, your account is basically frozen. We don't get to see anything you've been working on. So good habit, always, always, always click that button. On the side here, we have explanation, example, and message center. So explanation tells you you're going to lose your question attempt because it's going to literally explain this problem. It's going to give you the answer. So it's not going to give you the answer and then let you come type it in. Sorry, not how this works. Example shows you an example of something similar to what we're looking at. I know it's a different figure, but same idea. We have a figure of a plane here. Here's a scale factor. It's going to ask us some questions about the scale factor, and we have to apply it. So we can close this. We can look at another example if we want to. We can also message our teacher directly from the screen. All right, let's go ahead and take a look at this section here. So we've been practicing what's called rigid transformations for the last 3 sections, which a rigid transformation, when we're talking about transformations in math, is how we move a figure around, we can say the screen, around a coordinate grid, so we can translate, meaning move it from right, left, up, or down. That's just a translation. We can rotate it or turn it, kind of like spinning it. We can also reflect it, and you can think of that as like looking in a mirror. It's a perfect image, but it's the opposite. It's a mirror image, so it's backwards. Those are all rigid transformations. What that means is it doesn't change the size or the shape of the object. It stays exactly the same size or shape. It just moves. Now with dilations, this isn't rigid anymore. With this, we're going to change the size of the shape. So with this one, we have a scale model of a table, and it's 1 centimeter represents 9 inches. So here's the scale model of a table. It's kind of like a little dollhouse table. It's a very teeny tiny table with 1 centimeter. And every centimeter on this little tiny table represents 9 inches in the real world or on the real table. So this is telling us this is the scale we're going to use. And it says down here in the scale model, the length of the table is 4 centimeters. What is the length of the real table? So I'm going to be, very silly here, and I have a table. I'm not very great with my artistry here, but we're going to pretend like I'm not drawing a very wonky looking table there. I'm not really sure what happened. I think that leg should go over there probably. Something like that. We're going to pretend like that's a nice looking table. So the length is 4 centimeters. 4 centimeters. So I have 1, 2, 3, 4. If I broke this up into 4 pieces. 1, 2, 3. Oh, I drew 4 lines. It would help if I were paying a little bit more attention. There we go. There's 4 pieces. 1, 2, 3, 4 pieces. Right? 4 centimeters. 1 centimeter each. Each centimeter represents 9 inches. So each one of these is actually 9 inches in the real world. So I could use something like this to convert these. I can say, oh, well, 9 times 3 or 9 times 4, that's going to get me 36 inches. Instead of 4 centimeters, it's 36. But instead of having to draw this out each time and actually divide it up this way, because it's not always easy to do it this way, what we can do is we can use this scale factor. So 1 centimeter to 9 inches like this, and that's going to equal, we want to make sure I have centimeters on the top, inches on the bottom. So 4 centimeters, and this is the model on the top. So here's the model, and then the real thing is going to be on the bottom. So I don't really know, and I'm going to change this. I just realized it's writing really tiny. I guess I can wait a second. So I don't know what the real one is, so I'm just going to use an X or whatever variable I feel like using. So now I'll go ahead and increase the size here. I had this zoomed in earlier, so that's why I made it smaller. It looks very like a pencil almost. So now I'm going to use cross products or cross multiplication. So 1 times x, I'm going to leave the centimeters and inches out. So I just have 1 times x, which is x, equals, and I'll use pink, I guess, for the other side, 4 times 9, which is 36. And this would have centimeters and inches, and this guy would have just centimeters, like that. So they would kind of cancel out. The centimeters would cancel out because there's centimeters on both sides. So they would go away. So I'm looking for just inches. But x was inches, right? We already knew it's on the bottom. It's going to have inches on it. So this is the idea of dimensional analysis where we're carrying units through. But that can be a little confusing when we actually carry each unit through if we have multiple pieces to look at here. All right, so this is 36 inches. So down here it says the height of the real table is 18 inches. So now we have the height of the real table. And this is going to be a very bad drawing. It should be to this edge here, not to that other edge, but because that's more of a width. So I'll go like this. The height of the table is 18 inches. This is the real one. So I need to bring this back down to the model. It wants to know how big is the model. So let's use the scale factor again. We have 1 centimeter to 9 inches. That part doesn't change. That's going to be the scale throughout this whole problem. But now I don't know what the centimeters are. I do know what the inches are. It's 18 inches. Like this. So now I'm going to use cross multiplication. 1 times 18 gets me 18, and it would have centimeters and inches on it, but we're going to leave that off for now. And then I have 9 times x, which is just 9x. I want to solve for x because I want to know what is x. So I'm going to divide by 9 on both sides. And I'm going to have 18 divided by 9 is 2. So there are 2 9s and 8. We could also think of that. How many 9s are there here? There are 2 of them. So that would mean each one of these 9 inches is 1 centimeter on the table. So that's why it's 2 centimeters. So again, kind of a visual way to think about that, breaking it up, and the algebraic way with our cross products. All right. So let's get a new screen here so I don't have to rewrite all this. All right, so the table below gives the dimensions of a painting and a scale drawing of the painting. Find the scale factor of the drawing to the real painting. So this is important. We want the drawing to the real painting. So there was a drawing done and there's a real painting done. So this is kind of the model. This is the real thing. So make sure when you're doing this that you have the drawing figures or measurements on top and the real ones on the bottom. So pay attention to the way it says this to this. The first one goes on the top, the second one goes on the bottom. All right. So we want to just take a look at the scale for each one. We have length and we have width. So if we look at the length, we have drawing is 8 and the painting is 40. And we just want to reduce this. We don't want to turn it into a decimal. We just want to reduce it. It can divide by 8 on both top and bottom to reduce it. So we get 1 over 5. So this could be the scale factor. Every inch on the drawing is actually 5 inches on the real painting. So let's make sure that it's the same way for the width. So we have the drawing was 7 and the painting was 35. So both of these we want to reduce. Can divide by 7. So we get 1 over 5. So they do match. Perfect. That's what we wanted them to do. So that's definitely the way that works. Every inch on the drawing is actually 5 inches in real life. And sometimes scale, having a model of something makes it a lot easier to visualize it first before we go and make the real thing. So a lot of artists do this too, where they have sketches and drawings and they plan things out before they go and do this massive painting. Because if they didn't plan it out, it might not turn out exactly the way they had hoped, because they didn't put enough forethought into it. And a lot of things are like this. There's actually scale models that little kids play with. Hot Wheel cars, I don't think they're perfectly models to the real cars, but a lot of them are pretty darn close. They have opening and closing doors and the hoods open and close. They're little tiny models of cars. So the only problem with those is, like I said, I don't think they're necessarily perfect models. They're not exactly the same, but they do, function the same way. But a lot of big, even buildings before they're built, they make a scale model of it first so they can conceptualize it, they can see it before they go ahead and make the whole big building. All right, so we're going to go to the next one here. We're actually going to look at dilation on the screen, and Alex has this really cute little special tool to help us do this. So for the figure below, do a dilation centered at the origin with a scale factor of 1/2. So what this means is when we have a dilation of 1/2, if it's a fraction, we're cutting that object in half. We're dividing. That's what this means. It's going to be half of the object. So if it's a number less than 1, it should be smaller than the original. It's a fraction of the original. If it's a number larger than 1, that means we're increasing the size. It's greater than the original figure. So just definitely pay attention to those two pieces. So if we have the dilation, 1 means kind of 100% or the entire object, and we want to bring it down to half. So I want to go, that's half right there would be that middle mark there, because this is 1, 2, 3, 4, so half of that would be 2. So I want to bring it kind of into the middle there. So this is a half dilation. Now I need to go through and find my points here. So my top point for the original was 2 and 8. And the bottom one was still 2 and 6. And if we think about this before we look at the coordinates real quick, if it's half of the original figure, the coordinates are also going to be halved. So I can just take these and I can divide them all by 2. That's what 1/2 means. I'm dividing by 2. So I would have 2 divided by 2 is 1. 8 divided by 2 is 4. 2 divided by 2 is 1. And 6 divided by 2 is 3. So let's go ahead and take a look and see, does this actually work out? X coordinate of 1 and 4 for the top. That did work. X coordinate of 1 and 3 for the bottom. So that idea, that's the rule. We want to start to think about what is happening to these coordinates, because they're gonna ask us very quickly here to start doing this on our own without this little cute dilation tool. So it's very cool, this little slider, because it can definitely slide back and forth, and we can even see, it's getting larger, it's getting smaller. So we can play with that. If I have a number 1, that is the object. If I go to the right, it's getting bigger and bigger and bigger. So it's getting larger. If I have a number smaller than 1, it's getting smaller and smaller and smaller. Why can't I go below 0? How would I have less than 0 of the object? If I have 0 of the object, that means that it's gone. The object is no more. So you're not going to go below 0. You're going to have a fraction maybe, or you're going to have a number larger than 1. And you can keep going. This just goes up to 5. But we can keep going more than that if we wanted to. There isn't really a limit to the right, but there is a limit to the left. All right, so we're going to take a look at these pieces. And it says, draw the image of the figure following following figure after a dilation centered at the origin with a scale factor of 3/5. So 3/5, that is a fraction smaller than 1. So I don't think they're going to give you an improper fraction, but they might. You just want to pay attention to that. This is definitely a proper fraction. The numerator is smaller than the denominator. So this is going to be smaller. I already know that. It's a fraction smaller than 1. So I want to take each one of the points here. So each one of these there's 2 endpoints and there's 1 vertex here. So I have 5 and 10. So it's 5 and 10. And then I also have 5 and 5. And then I have 10 and 5. So 10 and 5. So here are my 3 points, and I need to dilate them. So I'm going to multiply by 3. Remember, fraction means multiply by the top, divide by the bottom. So I'm going to multiply both pieces by 3 and divide by 5. So 5 times 3, well, that's 15. And now I'm going to divide by 5. That brings me back to 3. So hopefully that made sense. I did 3 times 5, and I got 15, because 3 is the numerator. And then I'm going to divide by 5 because that's the denominator. So remember, fractions are just 2 things happening at once. It's multiplication and division happening at the same time. So now I have 10 times 3, that's 30, divided by 5, which is 6. So here's my new coordinate. I'm going to do the same thing with this one. 3 times 5 is 15, divided by 5 is 3. So it's going to happen the exact same way with the next one. I don't really have to do that. So once I know what it's going to be, I don't really have to keep doing the math. I've already done 5 and I've already done 10. So when I multiplied 10 by 3/5, I got 6. When I multiplied 5 by 3/5, I got 3. So they're using the same numbers kind of over and over again. Makes it really easy for me. I don't have to keep doing that same multiplication. So we're going to have 3 and 6, 3 and 3, and 6 and 3. Now I need to make sure I connect my points here because that's part of what they expect us to do. Boom. So now I'm going to click check, and we're good to go there. Yay! All right, we have one more of these. I believe we're going to look at the rule for writing a rule for dilations. So a dilation centered at the origin with a scale factor of 2 is applied to triangle RST. And the result is triangle RST prime, as shown. So the second one, they use these little tick marks to show you that it's been moved. So we have this original that's kind of light gray, and we have the darker blue or the brighter blue. That's the one that's been moved. So I can definitely see that the new one is bigger than the original. And that should hopefully make sense. We have a scale factor of 2. It's not going to highlight the 2, darn it, but scale factor of 2. That means it's 200%. It's 2 times bigger than the original figure. So it's definitely should be getting larger. So if we're using that same idea that we just did here, and I can multiply the coordinates, this one I multiplied and divided, or I just multiplied by the fraction 3/5. I do the same thing here. This one just has a scale factor of 2. So I'm going to take each one of the coordinates, and it's going to map to the new one. I'm going to multiply everything by 2. So negative 5 times 2 is negative 10. 2 times 2 is 4. So I'm just using these coordinates, and I'm just multiplying over here. 3 times 2 is 6. 4 times 2 is 8. Negative 5 times 2 is negative 10 again. And then negative 2 times negative 2 times 2 is negative 4. So I can go and I can confirm these. I can go negative 10 and 4. There's R. That's the R prime. That's the new one. And then we have T, so negative 10 and negative 4. That landed on T prime, which is exactly where we wanted it to be. And then if I do that last one, I have 6. Positive 6 is help if I'm going the right way. And positive 8, and that lands on S prime. So that rule does work. I'm multiplying everything by the scale factor, which in this case is 2. So I'm going to go down here and I'm going to look for that rule. Just shows me what am I doing to x and what am I doing to y every time. So I have x and y in each one of these. That's how we start out with x and y. And we're looking for the one that shows that we're multiplying by 2. So any of these where we have a fraction, we want to ignore those. We're not dividing by 2. That's what a fraction means, is division. So this first one, we do see it times 2, but it's only the y coordinate. Well, why not the x coordinate? They should both be multiplied by 2 if it's a scale factor. Over here, same problem. Now only the x is being multiplied. So this guy has a 2 and a 2, but the y and the x are in the wrong positions. There's no reason for them to flip positions on this one. This has to do with a reflection. And we're not reflecting this one, we're just dilating it. So here it is down here. We have xy, 2x, 2y. So this is the rule. We're multiplying by 2 each time here. All right, let's go ahead and click check. All right, so that was section 4. I will see you in section 5.